We'll look at a couple of other ways to represent continuous data. Again, we'll continue with the iris data set since it's nice, since it's open and it's convenient. But one of the take-home messages from the grammar of graphics is that it is always better to show as many of the data as you can, show as many of the raw data as you can. So a bar plot with an error bar is not all that interesting because all you know is the relative amount of variation, but you don't really know what the actual values were. When we plot the histogram, we know what the data were within the certain bins, and we can make the bins really small so we can see the individual data points. But there are a couple of other ways that are very useful to show the distribution of data as well. And one of which you are probably familiar with, which is the box plot, and the other is called the violin plot. But what we're going to do is to start with looking at a box plot. And remember, we looked at the 5-number summary last week, and so if we pick one of the variables from 5-number from the iris data set, then we know that's the median. This is the this 25th percentile, the 75th percentile. It's the largest value and the smallest value. About the distance between 0.3 and 1.8 as being the interquartile range. So 50% of the data are found in the interquartile range, from the 75th percentile down to the 25th percentile. Right smack in the middle, of course, is the median. So what we're going to do is to prepare a box plot, and we can use petal width just as an example. So what we're going to do again is to tell ggplot what our data set is going to be. And then in order to do a box plot, we have to have two different variables. We first have to have a variable that is going to be our factor, how we're going to separate out the different components of our plot. And so with iris, we have 3 different species, so we're going to do species there. And then for y, we're going to do petal width. So that's there. And R is pretty good about keeping up with the open and closed parentheses there, so it usually has the right number for you. And so now what we're going to do is to add our geome. So this time our geome is not histogram or density, but rather box plot. So fairly straightforward there. So let's run that. Oops. So there I have my box plots. And what I see is the interquartile difference is shown here. There's the median. The interquartile difference is shown there. So a very useful way to take a look at the overall distribution. And what you can see is that the interquartile difference here is mostly the region between the median and the 75th percentile. So that means we have a really steep portion to the curve here. If we were to plot the data along like a normal curve, we'd have a very steep side on the right side, on the left side of the curve. We also see that when you do box plots that occasionally some points are regarded as outliers. So they show up as points above the minimum or the maximum. And the definition of an outlier is a value that is more than 1.5 times the interquartile difference from the median. So what we would see here is that this number is so large, and this number is so large that we regard them as outliers. And so it might be worth your while to go back and take a look at your data set and see if you had a transcription error or some other error that explains why there's an outlier there. We can make our box plot look a little nicer, I think. So I'm going to use the black and white theme. So that's looking there. And what I can also do is I can fill the boxes with color if I want to. So what I'm going to do in this case is I'm going to just go into my box plot and I'm going to say fill equals and without even looking, I'm just going to say that I'm going to fill it up with red, and so we'll do that. And so a little interesting. What you can also do is to add a notch in your box plot where you have where the median is, so it becomes easier to compare the medians between boxes. So I'm going to say the notch is true. So all I'm going to do is type T, and now I have little notches. So these notches represent where the medians are. So the medians, it's pretty easy to tell the medians here and these three here, but oftentimes they might be very close together. So that can be a useful way to modify your box plot. So, and again, I can go through and I can change my my labels. And I can add a title. Can do all those sorts of modifications to make my box plot look a little nicer. And again, remember, if you want to look at it up close and personal, you can zoom in on it like so. And then again, if you want to save, if you're ready to publish, you save. You can export it either by copying it to the clipboard, save as a PDF, or save as a JPEG or other compressed image like so. But let's look at a different kind of plot related to the box plot. It's called the violin plot, and it actually gives even more information on the distribution of the data. And what I'm going to do here is to notch doesn't mean anything in the violin plot, but everything else should be the same. So this time, instead of saying box plot, what I'm going to do is to type violin. And I get a variable that looks, I mean, a plot that looks like this. And of course, what you can see is that this shows the distribution of the data. So the data range from here to here, or from there to there. But most of the data are sort of falling in here where it's quite fat, or right down here. Most of the data are falling into this fairly narrow range right here. So it gives you a really good idea about the distribution of the data. So there are relatively few small Virginica here. Most of them have widths that are fairly high. The ones here are sort of most in the middle. Even fewer that are very high compared to the ones that are low. And then these dominated by the ones that are right around the middle, but they abruptly fall off down when you start getting pretty small. So that's a useful way of taking a look at data as well. And what we can also do is to adjust the level at which the data are plotted. So we can use something that's just called an adjustment. And if I start with an adjustment of 1, I get values that look like that. But this is equivalent to sort of the bin command that we saw in histograms. Let's go to 0.5. And now what I'm doing is I'm parsing the data at a finer level. And if I want to smooth it out, then I can make this number bigger. So it's sort of up to you as to how you want to best represent your data. But anyway, violin plots and box plots are both very useful ways to present data. And in a sense, you're showing all the data because you're showing the shape of the distribution by looking at a box with the 5-number system, the interquartile differences between the upper and lower hinge, or you're looking at the violin plot.